Hello everyone, welcome again to this video. So in this video we are going to continue on our exploration of definite integrals. So there are a few things which we have to consider before understanding to and trying to solve problems on definite integrals. So in the last lecture we had introduced some of the basic properties like the fundamental theorem which was used. Now I am going to state it formally. The fundamental theorem of integral calculus. So given a function fx which is integrable over some closed interval a comma b, let's say, and there exists a function g from R to R such that g dash x is equals to f of x, that is the derivative of g is f. Then the fundamental theorem says that a to b f of x dx is basically equals to g of b minus g of a, right? So this is the fundamental theorem of integral calculus, and this comes from measure theory actually, which is the Lebesgue measure theory, and you should learn it in higher notes and higher classes because it's a very advanced form of integration, and measure theory helps us in probability as well, which you shall also learn in advanced probability. But for now it is enough to know that given a function f of x, which if it is integrable over some closed region a comma b in one dimension, and there exists a function g such that the derivative of g is f, or in other words if f has an antiderivative, then the fundamental theorem of integral calculus says that a to b f of x dx would be equal to g of b minus g of a. So to make that account, we also need to know how to set limits. How to set limits in case of a substitution. And by substitution I mean method of substitution, where we usually substitute for one variable, right, in case of substitution. So let us take an example. Suppose I is equal to 2 to 3 2x by 1 plus x square dx. So this is our given definite integral, and if it was an indefinite one we could have done it easily, but we are not really trying to rely on indefinite integration to solve problems of definite integration, like first evaluate the antiderivative and then put back the function, and not like that. So suppose you do not already know about the indefinite integration, and you just know the methods of it and you want to evaluate it directly. So first of all you have to notice that ddx of 1 plus x square is just 2x, right? So obviously a substitution of u equals to 1 plus x square makes sense. Therefore and the substitution would be t equals to 1 plus x square, okay? Then d of t would be 2x dx. So up to this part it is quite similar to as of that indefinite integration, but now the fact is that we also have limits in integration, and these limits are for x, right? So it means that the limit for the variable x is 2 to 3, and what that means for the new variable t, that's what we are going to trying to find out, right? So when x equals to 2, we just need to put the value of x to find out the new limit for t. So it would be 1 plus 2 square, or it would be 5. And when x is equals to 3, t would be 1 plus 3 square, or it would be 10. Okay, so this means then we have, and remember, in case of indefinite integration, at the end we used to put back all the values, but in definite integration there is nothing like that, because it basically represents an area, right? So as we go along, we are just trying to find the number which represents the definite integral. We do not need to find any function. So this means that the new integral, which previously was something like this, 2 to 3 2x by 1 plus x squared dx, with the new variable of integration and the limits 5 to 10, and 2x dx would be dt, and this should be t, will give you, and the derivative is ln of t, antiderivative of 1 by t, and the limits are from 10 to 5, so it is ln of 10 minus ln of 5, but this would give you ln of 10 by 5, or in other words ln of 2, which is the answer. So the limit changing is a procedure which can be evaluated just by we use equations, and we put the value of the lower limit and the upper limit separately in the new variable to find out what that value corresponds to the new variable. So if you have like the limits as f of x and g of x, and your new variable is like something in the form of that, you just put in the limits value in the new variable in place of x, or whatever your integration variable is, and whatever value you get for the new variable is your corresponding lower limit or upper limit. To illustrate the fact, let us do one more example. So suppose this was our integral that we needed to find, 0 to 1 1 plus x whole cube dx. Now in this integral, one way as always is to expand 1 plus x whole cube as 1 plus x cube plus 3x square plus 3x, and then integrate it separately, right? Another way is to make the substitution, y equals to 1 plus x. Obviously this would give me dy equals to dx, but the limits won't be the same, because the limit for y lower would be equal to 1 plus x lower, which is 1 plus 0, which is 1, and similarly the limit for y upper would be 1 plus x upper, and this should be equals to 1 plus 1 equals to 2. Then the new form is I equals to, and the limits would be 1 to 2, and this should just be y cube dy, right? And now we know the antiderivative is y to the power 4 by 4, and it's from 2 to 1, basically 1 to 2. If you put it in the values, you get 2 to the power 4 minus 1 to the power 4 by 4, right? So 16 minus 1, it's 15 by 4, which is our required answer. So see, if we had done it the other way by expanding, it would have been a bit too messy, but in this way we can get the answer directly. So definite integration is a whole lot easier if you know the properties. And talking about properties, let us do a few properties of it, and we will prove them as well. If a to b f of x dx so a to b f of x dx equals to a to b f of a plus b minus x dx. This is a property, so let us prove it. Now to prove this kind of a property, we need to understand that this looks like f of x becomes f of a plus b minus x, which is not true, but it is true when they are inside the integral. And this also gives you a rough idea that even if two integrals are equal with the same limits, it does not necessarily mean the function inside them has to be the same. Two different integrals can have the same value, and yet the integrand or the function which you are integrating may be completely different, right? Okay, so how to prove it? Let us denote the integral. That integral be a to b fx dx. Now what we can do is we can make a substitution. Substitute x equals to a plus b minus y. In this substitution, what we get is dx equals to minus dy, right? And the limits would be something like this. So this would be the lower and the upper limits, and therefore the new integral would be a to b, and now it becomes b to a, and it becomes f of a plus b minus y, and there it becomes minus dy, right? So in other words, it becomes minus b to a f of a plus b minus y dy. Now there are two things that needs to be known in here, which I'm going to say. First of all, remember that a to b fx dx is the same as minus of b to a fx dx. So this can be proved in a very easy way, because you can see that let us assume that g is differentiable and g dash x equals to f of x for all x belongs to a comma b, right? Then a to b f of x dx should be equals to g of b minus g of a, right? Why? Because by fundamental theorem of integral calculus, by FDIC. And similarly b to a fx dx should be equals to g of a minus g of b, right? And this proves that so this is one of the proofs, right? Now another property that we'd like to prove is that the definite integral is independent of the variable. Right. So what it means is that a to b f of x dx is the same as a to b f of y dy, and this is also same as a to b f of z dz, because it doesn't necessarily matter what variable's name you're using, because as long as the limits are numbers a to, which are like real numbers a to b and not a function, this answer, this function f of x dx or f of y dy or f of z dz, all of them will evaluate to the same thing, right? Because at the end of the day, if f has an antiderivative, it will be given as g of b minus g of a, all of them, because it doesn't necessarily matter what variable name you are using, right? So using these two properties, we have that so remember, in the here we were trying to prove this. So I equals to a to b f of a plus b minus phi dy, and it became minus a to b f of a plus b minus phi dy. So we had proved that I equals to minus b to a f of a plus b minus y dy. But then again, as I said, the minus b to a, whenever there is a minus in front of a limit of integration, the limits just get reversed, so it becomes a to b f of a plus b minus phi dy. And you know that definite integrals are independent of variables, so it doesn't matter if you put a y or a x or a z here, because it's completely independent. So you can write it as well as f of a plus b minus x dx. And since I was already given as a to b f of x dx, right? So yeah, this is one of the properties, and this property would be used extensively in lot of problems when we will be solving problems actually. But now it's time for doing some more of the properties here. Like, first of all, if f is an even function, it becomes 2 into 0 to a f of x dx, right? And if f is an odd function, then this integral is 0. Now this is a question that that can be answered either using graphs or by using the properties of integrals. So since we are trying to avoid the graph theory right now, because we also need to know how to transformation of graphs work in case of even and odd functions, since we do not know that stuff yet and we haven't learned it yet, we are trying to focus on more on the properties of integrals to find this out, which is our basic goal here. So proof so what does an even function mean? So I'll write it down for both of this. So an even function means that f of x would be equals to f of minus x for all x belongs to the domain of f, where f is a function from like domain to real numbers, let's say. And for odd functions, like this. So there are a lot of examples of even and odd functions, like let me give you some examples. F of x equals to x square. It's an even function because f of x is equals to x square, which is also equals to minus x whole square, which is also equals to f of minus x, right? Whereas f of x equals to x cube is an odd function, since f of x equals to x cube equals to minus of minus x cube equals to minus of minus x whole cube equals to minus of f of minus x. Now the property that we were talking about, let us do it like this for the even part. And in doing so, we are going to learn another property which is like this. If f of x is integrable, and the region is divided as a less than c less than d less than b, then so it doesn't matter in how many regions it is divided, or you can divide it in as many regions as possible. So this integral a to b fx dx can always be written as a sum of integrals, which is a to the next number c fx dx plus c to the next number d fx dx plus d to the next number b fx dx. So basically what I'm trying to say is, if we were to evaluate the integral 0 to 3 x square dx, you can write it as 0 to 1 x square dx plus 1 to 2 x square dx plus 2 to 3 x square dx, like this, right? So in our given problem, what we can do is I equals to minus a to plus a f of x dx, and we can separate it into two parts, which is minus a to 0 f of x dx plus 0 to a f of x dx. Okay, now this part is already there, and we need to prove that this I is twice of this, so we need to prove that this one is also equal to this one. So let us denote by j, and let us evaluate j alone. Minus a to 0 f of x dx. Make the substitution. So we make the substitution y equals to minus x, where dy would be equals to minus dx. This would give us, I'm going to figure out the limits later. Firstly, it would mean that this is equals to f of minus y, and dx would be minus dy. And as far as the limits, y lower should be minus of x lower, which is basically plus a, and y upper should be 0. So this should be like from a to 0. Let's bring the minus in the front, and we have minus a to 0 f of y d of y. So the minus reverses the integration limits, so this one will become 0 to a f of y dy, and since it is independent of the change of integration variables, it will be 0 to a f of x dx. Therefore I is equal to 0 to a f of x dx plus 0 to a f of x dx, which is basically 2 times 0 to a f of x dx, right? So this concludes this problem, and in the next video we shall do about the function of the part where we have discussed about the odd function. So I hope you like this video, and please continue on watching to learn about the whole thing, learn about how do we complete the integration part here, because we're going to do a lot of interesting things, such as we would be trying to evaluate some of the functions which cannot be expressed in terms of elementary functions, and some series of historical importance as well. We'll be discussing a lot of them very soon. So thank you for watching this video. I'll see you in the next video, and meanwhile do check in the link in the description for the Breatter Maths app, where you have all these video lessons and lectures included. Thank you.